So the first session will be introduction to the fundamentals. Okay, hopefully you can see my screen. And here we go. So this initial session will basically explain what's the IEA's approach to energy statistics and energy balances. Now, because we are an international organization and we collect data from many different countries, it is essential for us that the data is coming in kind of common standards across the countries, so that we can be comparing across the countries and so that we can also simply understand each other. So it's important to use common terms, common definitions. The IEA approach is to use the International Recommendations for Energy Statistics, which is an internationally agreed system by the UN Statistical Commission, published in 2011. And this is the reference that we use, and we encourage also all the countries to use it. IRES, which is the acronym for International Recommendations for Energy Statistics, has been translated into the 6 official languages of UN. So you can go to the website that is provided, download it, including in the language that is convenient for you, and use that in your everyday work to be consistent with the way how the IEA, but also UN or Eurostat, for example, do energy statistics. Now, let's talk about some basic concepts that are referred to in IRES. What's really important, it is to define the scope and the boundaries of energy statistics. So for that, we use a few basic energy concepts, such as energy products, flows, production, definitions of different sectors, etc. Why is this important? It's important so that we are all able to speak the same language and come up with comparable data. Now, energy is a relatively wide concept. Energy is observed all around us, and that's, for example, in form of light, heat, chemical energy, kinetic energy, etc. However, not all of the energy is included in energy statistics. Generally speaking, energy that does not have direct impact on society is not measured or is not part of energy statistics. So as an example, the sun shines on all of us every day, but if that sun doesn't fall, for example, on a photovoltaic panel that then produces electricity, if it just falls on the ground, we don't account for that sunshine in energy statistics. So it's quite important to draw these boundaries, because otherwise, it's really hard to know what is it that we need to report. So coming from this logic, energy products then are forms of energy which are suitable for direct use for human beings, so such as coal or oil or gas. You can directly burn, so through combustion process, extract energy from them, or electricity is directly usable for energy production. Now, I think we have someone that we cannot mute on our end.
It's muted.
It's muted? Okay, excellent. So energy flows. Energy flows, we have many different energy flows that we track in energy statistics. The typical ones are production, trade, transformation, and final uses across many different sectors. The flows are defined by the International Standard Industrial Classification of all economic activities. And this is comparable across many different kinds of statistics. Then what is production? Production is a very important concept. And we will talk about it a little bit later. What's important to track in production is, for example, whether the energy produced is produced as through entities whose primary activity it is to produce energy or who have it as a secondary activity. It's also important to track whether the energy is for sale or for own use, etc. Energy sector. It's really important to distinguish energy sector from industries. The way how IEA does energy balance is that energy sector is the sector that, of course, does the transformation of one form of energy to another form of energy, but it's also a sector where we are tracking its own use of energy, and it should be reported separately from the use in other industries. And then the last thing that we want to cover on this slide is the reference territory. So in particular, for countries that, for example, have many islands, it's important to be very clear in what you are covering in your energy statistics. Typically, countries try to cover the entire national territory and report the energy used based on physical availability on this territory. The territory does not include only land, but includes also airspace and territorial waters. So it's important to try to cover all of these. Now, in certain cases, for example, when you know that a particular island, for example, of your territory is not covered, then it's important to at least report the fact that it's not covered. So now, how do we bring all the statistics together? So as you may know, IEA collects statistics for different fuels. So for coal, oil, gas, renewables, we have separate questionnaires, at least for OECD countries, that collect basically the situation for these fuels. And then we bring all of this together in an energy balance. The energy balance is there to compile all the data from different sources in a single table and provide basically a summary for the given country. Now, if that summary is to be meaningful, you can imagine that we need to bring all of these different fuels under common units so that we are speaking about comparable units. So how does that work? Energy balance is basically a matrix, a two-dimensional, of products and flows. Within IEA, we put products into columns. So in columns, then we see basically commodity balance for a given product. And then different rows will be flows such as energy production or trade, or then in the transformation sector, we have, for example, oil refineries. And then balance is called balance because things in this table need to balance both horizontally and vertically. So you will see that we have at the end, the last column is column called total. So that's the column that sums up across all the products. And so that gives us, for example, an idea of what's total energy production in the given country or what's total trade, etc. Now, on the side of flows, we do not have, sorry, let me stay here. On the side of flows, we don't have the row that is called total. It's balanced in a different way, and I'll talk about that in 2 minutes. Let me first go to the definition of different products. So under IRES that we talked about, there is a classification of products called standard classification of energy products. So that's, we refer to it as SIEC, Standard International Energy Classification. And this classification basically classifies all energy products into 10 large categories that you can see on the slide, and then each of the categories has further subcategories. And this is what is currently used within the IEA, but also UN and other places that use IRES as the basis for doing their statistics. Now, these classifications are regularly updated. We are currently working on the process of updating the current classification because as energy field is changing, for example, things like green hydrogen or ammonia are coming much more to the picture. We need to include them in the standard classification so that we can trace them in the energy balance. So that update process is currently underway, and in the next year or two, we will have a new, slightly changed SIEC classification. Now, let me go back to how does the balance through the flows in the energy balance. So part of the flows is what we call supply. So there you will have your standard production, trade, stock changes, and then international bunkers. That when you sum up across those rows, so basically bring you total primary energy supply to the country. And then from that supply, of course, you will be serving different energy services within the country. The first thing that will happen is that some of the primary energy sources will be transformed into secondary energy sources. So, for example, that will happen in the transformation sector. You will have crude oil that goes into oil refineries and will come out as oil products. It's your typical transformation process, and that is reported in the transformation of energy. While then the final use of oil products, for example, oil products that go into transport, will show in the part that is final consumption. Now, that means basically that you have supply side on top of the balance, and demand side is basically the sum of the transformation sector and final consumption. And we will talk about how these two meet in a second. So as I already said briefly, the first block is energy supply that ends up in total energy supply in the country if you sum up across all energy products. But in this part, you can also see the details of trade, bunkers, and stock changes. Could you please mute? Then in the second block, we have the transformation sector. So here, this is inputs and outputs into electricity plants or heat plants, oil refineries, coal transformation, etc. What's important to note in this section is that here you will see inputs with negative signs and outputs with positive signs. So the example that I already mentioned, for example, in oil refineries, you will see the crude oil goes into refineries, so it's noted with negative sign, while oil products then come out of the refinery, so it's a positive sign. And that way you can see what's input and what's output. So basically, in the transformation sector, we are transforming energy sources from primary to secondary, and then in the final consumption sector, they will get used. So, for example, in electricity plants, in the transformation, you will have input, coal, and then in electricity plants, you will produce electricity. So output will show in the electricity column then with a positive sign. And we have already talked about the refineries. Now, what this means, because we are showing inputs and outputs, and because everything is in the same unit, we can also see basically very quickly what is the efficiency of this transformation. So if you divide output over input, you will get an efficiency number. If the number is over 100%, you know that there is something very wrong with your energy balance, and you should go and check where is the error. For many of these transformation processes, we know what are kind of the standard values that you would want to see. So for us, we can very quickly check whether the numbers that are reported to us make sense, or whether we should go back to the country and ask questions. Now, what's really important is to distinguish transformation from own use in the energy sector. So here we take, for example, an example of oil refinery. So oil refinery takes as an input crude oil and then produces oil products out of it. But oil refinery itself has its own energy needs. So there is lighting needs in the refinery. There is possibly heating needs, depending on in which country it is. So if these needs are satisfied by crude oil itself, they should be reported. They should be separated out basically and reported as own use of the refinery. Now, of course, it's entirely possible that the refinery is actually, for example, buying electricity from the grid and using that for lighting. But what's important is that the transformation numbers and the own use numbers don't get mixed up. So reporting of energy own use is very important for us. Now, the last block is the block of final consumption. So final consumption is when energy products are consumed in different final sectors. So the three kind of very large categories are industry, transport, and then consumption basically mostly in buildings, so such as residential, commercial, and public sectors. And then also some consumption in agriculture, forestry, fishing, etc. Here we are showing industry and transport, basically just at an aggregate level. When you are dealing with a detailed energy balance, then you can go into details of industrial sectors and show many different sectors and their individual consumption. Similarly, for transport, you can divide further into road, rail, etc. What's really important to note here is the very last row, which is non-energy use. Now, what is non-energy use? Non-energy uses are to be reported in particular for fossil fuels. And these are uses where the fuels are used as raw material, and basically they're not combusted, but they're transformed into another material. So you could imagine from fossil fuels, production of asphalt or plastics or fertilizers. So these, of course, do happen, but your road or your plastic cup is not an energy carrier, and therefore the uses of fossils that are ending up in these materials are to be reported in non-energy use. This is very important because, as you can imagine, once you are using energy balance to do, for example, CO2 statistics, then because these materials will not be combusted, they will not emit CO2. And so it's really important to note these properly. There is one difference between fossil fuels and non-fossil fuels. For non-fossil fuels such as biomass, the rules, at least what we have at IEA, is that you are not to report non-energy uses of biomass even in the production, which is quite logical at the end. So all the wood that is out there for other purposes than energy purposes, so for example, wood used for furniture, does not appear in the production line of energy balance, and therefore naturally you will also not report it in non-energy use. And so the non-energy use for biomass in standard energy balance of IEA should be 0 because we don't start with reporting on furniture to start with in the production line. Now, let me sum up quickly what are the main energy flows. So basically, on the supply side, we have the production, trade, the bunkers, and then on the demand side, we have spoken about the transformation sector, own use of energy sector, and total final consumption in different end-use sectors. And the difference between the two large blocks of supply side and demand side is what we call statistical difference. Now, if you are measuring supply side separately from your measurements of demand side, it is very normal that you will end up with slightly different numbers. So the statistical difference will be non-zero. If your statistical difference is very, very large, then maybe some of your measurements, I would think typically on the demand side, which is harder to measure, maybe some of those are non-ideal, and maybe you need to be checking on where the possible errors occurred or whether you didn't forget about certain uses, etc. Now, if the statistical difference is 0, that's suspicious because no measurements are that precise. And therefore, we would conclude that some of your uses were probably simply calculated because you couldn't measure them. And we would typically send you questions about that, why such uses couldn't be measured or where is the issue. But basically, statistical difference, we would expect it to be small, but we would expect it to be non-zero if all of your supply and demand side statistics are measured. Now, a few practical reminders on conversions, because over the next 4 days, you will hear quite a bit about them. So energy statistics involves various variables and units. So we have units of mass, kilograms, tons, etc. Units of volumes, liters, barrels, meters cubed. And then energy units at IEA, we oftentimes use kTOEs or terajoules. And now switching between these units is sometimes standard. So conversions involving the same variables, so energy to energy, those are fixed. And you can be going to our units converter and find them there. While conversions from mass to volume may vary depending on densities. So different fuels will have different densities. And the trickiest ones are conversions from mass or from volume to energy. These will require product-specific calorific values. Now, calorific values on themselves can differ even for a given product. So calorific value is basically the heat energy obtained from 1 unit of fuel when it's burned. We would expect for different fuels that these calorific values fall into certain ranges, but these ranges can be relatively wide. They will differ based on the origin of the fuel. But even within the given country, they may differ still based on what is the consumption, the type of consumption for the given fuel. So for example, you can be mining for bituminous coal in your country, and that bituminous coal will have a particular calorific value because it comes from your particular mine. But you can export part of this production, and for your own uses, you can import some bituminous coal from a different country that you will use for a particular use, and therefore that one will have a different calorific value. And then if you know about that, it's important to report that different calorific value so that when we are working on energy balances, we can reflect this properly. Now, why are we doing energy statistics at all? How is this useful? So it is useful for policymakers, of course. Policymakers are formulating energy policies, and then they want to monitor the impact of these policies. So energy statistics helps with monitoring of impact. Energy statistics also helps with monitoring of national energy security, which is one of the basic missions of IEA. Energy statistics helps with planning of different industry development. So, for example, if you want to be setting up, I don't know, your own solar panel production in the country, you may want to know how much of PV panels are installed in your country and are going to be installed, so that you know whether you will be serving your own market or whether you should prepare for exports, etc. Then last thing is that there are also policies beyond energy, such as health, climate, or environment, which can be partially tracked using energy statistics. Now, beyond policymakers, there are other important stakeholders that care about energy statistics. Will be your business community, so people that are, investing their funds into different energy uses or into different industrial uses. So energy industry as well will be interested in energy statistics. International organizations such as us, but also, for example, development agencies that are helping with deployment of energy installations globally will be interested in this. Academia, of course, and in certain cases, even general public. Then the basic energy statistics and energy balances help us with development of different indicators that are related to energy, but also different economic, social, and environmental dimensions. So here we're showing a few examples of such indicators. And then in the practical use of these, you can, for example, trace things like total energy supply per capita on the planet. Is that increasing, decreasing? Total energy supply per unit of GDP. It's good news to see that it's decreasing. That means basically that the energy intensity of creating GDP in the world is going down. So for 1 unit of GDP, you need slightly less energy today than you needed 20 years ago. It's very good news. But then another very important thing that we can do once we have fully done energy balances is to estimate CO2 emissions from fuel combustion. This at the IEA, we are using our energy balances and then IPCC methodologies to come up with CO2 emissions. And one of my final slides is that energy statistics and energy balances then support tracking, for example, energy efficiency, though oftentimes for that we require much more detailed data than just final uses as they show in energy balances. So we would, for example, want to know for residential use how much of energy or how much of electricity in the residential sector goes to lighting, how much goes to space heating, how much goes to appliances, etc. So that becomes a little bit more complicated, and oftentimes this requires actually surveys done on the ground to come up with these detailed statistics. So our main objective and collective objective is basically to maintain policy relevance of energy statistics. So we don't do it just so that we have the data, but so that policymakers can use them for different uses that they need for tracking their energy policy in the given country. Now, you will hear more about all of these topics during this week in the detailed sessions that will follow.